Just 2 years ago, NASA dispatched a dishwasher-sized box of lasers nicknamed as the Engineered Quantum Mechanics Box up to the International Space Station, which is a habitable artificial satellite orbiting 400 kilometers from the Earth. The goal behind this effort was to create a bizarre fifth form of matter that's not even found in nature. At this point, all I was thinking was, is there even a fifth state of matter? If you're wondering the same, then hype up your burning curiosity, as we are just about to dive deep into this phenomenon. It all started in the year 1925, when a young Indian scientist, Satyendranath Bose, sent Einstein a scientific paper he had written. The same paper which was once disqualified for publication. Well, not everyone knew this paper was seminal in creating the very important field of quantum statistics. Before we explore the great minds of Bose and Einstein, let's get our basics sorted first. And to help us with that, we have very important friend with us today.
Hey guys, I'm a photon. I don't think I would need a separate introduction, as I already know how significant and famous I am in the field of science. I am the basic unit of all light. I am here to talk about the two types of elementary particles known in the entire universe, bosons and fermions. Being a bosonic particle myself, I would proudly say that we were named after the great Indian scientist Satyendranath Bose by Paul Dirac to commemorate Bose's contribution in developing the Bose-Einstein statistics along with Albert Einstein. One of our main characteristics is that we possess symmetric wave function which remains invariant under identical particle interchange. We have zero or integral values of subatomic spin. The one thing we hate is being disciplined by principles and laws, and therefore we disobey Paul's exclusion principle, which means more than one of us can exist in one quantum state. The Bose-Einstein statistics, which describes one of the two possible ways in which a collection of non-interacting, indistinguishable particles may occupy a set of available discrete energy states at thermodynamic equilibrium, apply exclusively to us. As the statistics developed by Bose in collaboration with Einstein is only applicable to particles that do not obey the Paul's exclusion principle restrictions. There are also no conservation laws governing the total number of bosons in any process. We can be created and destroyed freely in process. Apart from photons, gluons and mesons are some of the particles classified as bosons. On the other hand, fermions are the exact opposite to us. The term fermion was coined by Dirac, who named them after a famous scientist, Enrico Fermi. Fermions include particles in the class of leptons, for example, electrons and muons, in the class of baryons, for example, neutrons, protons and lambda particles, and also nuclei of odd mass number, for example, helium-3 and uranium-233. They possess antisymmetric wave function under identical particle interchange. They also have half-odd integral spin values like half, 3/2, etc. Not more than one of them can exist in a particular quantum state as they obey Paul's exclusion principle. The Fermi-Dirac statistics, which is a counterpart of Bose-Einstein statistics, applies exclusively to fermions. There are also strict conservation laws regarding the number of fermions in any process. I've been talking for so long, it's really hard to stay at one place, I have totally hit my limit now. I'm gonna take off, humans. Bye.
Thanks, buddy. We really appreciate this. So after a quick glance at the elementary particles, I believe it's now safe for us to talk about the exact work of Bose and Einstein together.
There has been no other scientist in the world other than Satyendranath Bose whose name is indissolubly linked with Albert Einstein in physics textbooks. This is simply due to Bose-Einstein statistics, which revolutionized quantum physics and led to the greatest scientific discovery of this generation, the Higgs boson, popularly known as God particle, and the Bose-Einstein condensate. Bose joined as lecturer in the physics department of the University of Calcutta in 1916. During this time, he and Professor Meghnad Saha translated Einstein's works on general relativity into English from German and published them as a book. In 1921, Bose joined the physics department of Dhaka University. In 1924, while presenting a lecture on the theory of radiation and the ultraviolet catastrophe, Bose intended to show his students that the contemporary theory was inadequate because it predicted results not in accordance with experimental results. He had been very dissatisfied with the way Planck's quantum law of energy distribution was being derived. Earlier, Ludwig Boltzmann had developed mathematics using probability and statistics. Bose, for the first time, took the position that the Maxwell-Boltzmann distribution would not be true for microscopic particles, where fluctuations due to Heisenberg uncertainty principle will be significant. Thus, he stressed the probability of finding particles in the phase space, each state having volume h cube and discarding the distinct position and momentum of the particles. Bose applied this statistics in a novel way to predict the number and probability of Einstein's photons. Bose adapted this lecture into a short article called Planck's Law and the Hypothesis of Light Quanta and sent it to Albert Einstein. Einstein translated Bose's paper in German and published it in Zeitschrift für Physik. Einstein adopted Bose's idea and extended it to atoms, and this led him to predict which now we call Bose-Einstein condensate. What Bose showed in his paper was that in the case of photons, classical statistics does not hold much relevance. It's a new statistics which is now called Bose statistics. He assumed that the photons are identical and indistinguishable, unlike classical gas molecules. This is the reply that Einstein made to Bose. Here, he confirms that the paper was translated by himself and recommended for publication. Bose's thesis was founded on the idea that photons formed a special class of particles which Paul Dirac later named bosons in his honor. Dirac and Enrico Fermi had separately realized that particles like electrons and protons formed a separate class since called fermions. Bose had only described the behavior of photons, which are massless bosons, in his paper. In 1925, Einstein extended Bose's book to include massive bosons in the theory as well, coming up with a broader framework of rules describing the statistical properties of bosons called Bose-Einstein statistics. And in its aftermath, Einstein quickly realized a peculiar implication. He found that should a gas of bosons be cooled to a particularly low temperature, they would all collectively occupy the lowest quantum energy state. One way to understand this is in terms of wave function. In quantum mechanics, the wave function is a mathematical problem whose solution yields the chances that a particle is present at a chosen point in space and time. In a cloud of supercooled bosons, Einstein predicted that all the bosons occupying the common state could be described by a single wave function, such that no two bosons could be distinguished by their properties. This isn't possible with fermions. If such a condensation of bosons could be recreated in a lab, physicists knew that it would expose the machinations of an invisibly tiny world on an unprecedented scale. And that's what Eric Cornell and Carl Weinman, both from the University of Colorado, and Wolfgang Ketterle from MIT, first perfectly achieved in 1995. The trio's work was a major boost for physics research as a whole, and physicists working with PECs to this day continue to uphold that bearing. We'll see exactly what they did shortly, but before that, let's address the question, how exactly is the BEC formed?
To answer this question, we need to understand a few basics first. Allow me to ask you a question. Suppose I give you 2 boxes and 4 white balls and ask you to place the balls inside the boxes in whatever combination you want. If I were to take a wild guess before you even place the balls inside the boxes, what chances are there for me to guess the exact combination which you have used? If I were a mind reader, then I would have no problem in finding out the combination, but otherwise my best option would be to use probability. So I must choose that combination which would be the most probable, or the one which you are more likely to choose. There are several ways to do it, but let's try this method. I'll first assume that the balls are all not white, but they are red, green, blue and orange, or any 4 distinct colors for that matter. Now let's try to see what possible combinations are possible by brute force. That is, we arrange them one by one mentally in all possible configurations. We find that there are 16 possible configurations, or 16 possible ways for you to have kept the balls. But wait, we also find that in some configurations, the number of balls in each box remains the same. For instance, the second configuration and third configuration both have 3 balls in the left box and 1 in the right box. Now, we try to see which ones would add up if the balls are the same color or white as is asked in the question. We find that now there are 5 possible configurations, and in these we see that the combination of 2 balls in each box has the most number of configurations under it, 6. So that would be the most probable combination, and hence that would be my choice. Of course, the truth is I only have a 37.5% chance of getting the correct answer, and I might be wrong. So you might ask, why should I use probability if after doing all this I might still get the wrong answer? Well, if you were to do this experiment hundreds or thousands of times and each time record exactly what combination you place the balls in, we'll find that you are most likely to use the 2 balls in each box configuration, or 2,2. Here, all the possible combinations for the white balls are our macro states, and all the possible sub-configuration of each macro state are our microstates. Our system has 5 macrostates and 16 microstates in total. The 16 microstates are divided into these 5 macrostates, each macrostate having some number of microstates under it. Often, the number of microstates under the macrostate is called its degeneracy. This number divided by the total number of microstates is what we call as the probability of that macrostate. Well, what if initially there were 2 balls and 2 boxes? Then, by using the multicolored ball approach, like we used just now, we see that there are 4 possible microstates which are divided into 3 macrostates, and the configuration 1,1 has the most number of microstates in it. Well, 3 balls and 2 boxes? Then there are 8 possible microstates separated into 4 macrostates, and we see that the macrostates 1,2 and 2,1 have the most number of microstates under them. So, we see that the macrostates which are the most probable are those where the balls are arranged equally. Without exactly proving it, I assert that now, how many ever boxes or balls there might be, the combination which will be the most probable would be the one where the balls arranged are equal the most. So, for 3 boxes and 12 balls, the most probable configuration would be 4 balls in each box, and for 100 balls and 10 boxes, the most probable configuration would be 10 balls in each box. Inherently, we see every problem of this sort can be attempted to solve if we count all the microstates and see which macrostate has the most number of microstates under it. The combinations are countable when the number of boxes and balls are small. But if there were millions of boxes and millions of balls, counting the microstates would be impossible. But why on earth would anyone have a million boxes and a million balls and try to arrange them in different ways? Well, here the analogy directly corresponds to atoms or molecules, to balls with discrete energy levels, to boxes within some confined system. In that case, we define a quantity which is a measure of the availability of all the possible microstates, which is called as entropy. Entropy is given as the product of some constant value, which is the Boltzmann constant, times the natural logarithm of the total microstates of the system. As entropy is a thermodynamic variable, the equation serves as a direct connection between thermodynamics and statistical mechanics. In reality, atoms or molecules of a material exist in discrete energy levels, and the number of particles in each such energy level depends on various parameters. Depending on the nature of particles, the number of particles in each energy level varies. The particles which we are interested in are like the white balls in different boxes. That is, indistinguishable particles in discrete energy levels. Those type of particles are called bosons, and they do not follow the Pauli's exclusion principle. For these particles, the number of particles n in some energy level I, n suffix I, is given as the number of degenerate states in the energy level I, which is nothing but the number of microstates for that particular macro state, divided by e to the power the amount of usable energy by kT minus 1. This kind of a distribution is called as Bose-Einstein distribution. In this simulation, we see that there are 200 balls or atoms which are confined inside a box, and initially they all have the same momentum, but as the time goes on due to collisions, the momentums of the particles gradually change and they get arranged in a form of a distribution, which is graphed near it. We see that in the beginning the particles have chaotic velocities or momentums, but as time goes on, the distribution given theoretically in the form of the curve actually matches with the velocities of the particles. This is one form of a demonstration of the Bose-Einstein statistics. The amount of usable energy here is nothing but the difference between the discrete energy of the level I, epsilon I, and the chemical potential mu. Here, we encounter a new term, chemical potential, which requires some form of definition. Roughly put, chemical potential is the negative rate of change of energy E with respect to change in the number of particles N. Its traditional definition is the amount of energy absorbed or released when particles enter or exit a certain energy level. The point of interest for us here is when the temperature of the system is reduced. The particles thus move to lower and lower energy levels as they lose energy and as energy is liberated. When particles enter into a certain energy level, they will tend to occupy the lowest possible energy level. This again is a direct consequence of the disobedience of Pauli's exclusion principle. Thus, when temperature is reduced, dou E by dou N is some positive value for bosons, and so mu, or the chemical potential, is negative. Exactly at the Bose temperature or the critical temperature T0, mu saturates and it becomes 0. At the critical temperature, the number of particles in ground state are given by N0 equal to capital N times 1 minus T by T0 per 3 by 2. But we see that at the critical temperature there are no particles in the ground state, and as the temperature decreases and tends to 0, almost all the particles move into the ground state. The particles condense together in the ground state, and this phenomenon is called as Bose-Einstein condensation. Let's try to visualize what happens exactly by watching a simulation. In the beginning, the particles are in different energy levels. Their energy levels are given by their colors. Brown denotes highest energy, red second highest, orange third highest, and so on, till white, which denotes ground state. As the temperature is reduced, we see that the particles fall from higher energy level to the lower ones, denoted by the change in their colors and reduction in velocity. They tend to lose their particle nature and become more like wave packets, the indeterminacy in their position increasing as the temperature decreases. And beyond the Bose temperature, all the wave packets combine together and form a single wave packet, as will be seen shortly. But before that, a small warning. This is a gross over-exaggeration. This is not what happens exactly. To illustrate it better, we have tried to make the particles look more transparent and try to increase their radius to suggest that they are now losing their particle nature and becoming more like waves. Here the wave packets lose their distinctness, and one cannot be distinct from the other. They all combine together to form a single quantum packet which simultaneously contains all the wave packets. Let's see if that happens. Now, as you can see, they've all combined together to form a single wave packet, and the particles inside the wave packet are now indistinguishable. We can't point out a single particle and say that its position is this. They all mixed match with each other and have now combined together to form a single wave packet. This is called as the Bose-Einstein condensate, or the fifth state of matter. One of the biggest milestones in experimental physics was the creation of this condensate by cooling liquid helium. How exactly that was done will be explained next.
A direct consequence of this condensation can be observed in a gas which is used to inflate balloons, helium. Interesting things start to happen when we cool this gas beyond a certain temperature. When we cool down the substance below a temperature a few degrees from the absolute temperature, it turns into a superfluid, which means that it can flow without any viscosity. The lack of viscosity simply means that it can flow up the walls of the container or it will leak through the cracks of the container. It sounds impossible, but with helium cooled up to minus 270 degrees Celsius, this is actually what happens. That's the critical temperature below which the matter makes it transition to a Bose-Einstein condensate. That is 2.17 K, the lambda point, the temperature at which normal fluid helium makes a transition to superfluid helium-2. Helium is unique among the condensed atomic systems since the bulk properties of the liquid are dominated by quantum effects. The most important of these are the statistical effects that arise for identical particles. For bosons such as 4 Ha atoms, there is no limitation on the number of particles that can occupy a single quantum state. A quantum mechanics explains how atoms or molecules cannot just have some energy, rather the energy levels are discrete. This is applicable to all the systems, but other effects outweigh the quantum one. But when you cool down the situation, it becomes a bit different. At low temperature, most of the objects freeze and become size. Helium is unique among this, which never freezes at atomic pressure. It remains a liquid up to absolute zero, which is minus 273.15 degrees Celsius. But things start acting strange when it reaches minus 270 degrees Celsius itself. Atoms start falling into lower and lower energy state, and more atoms fall into a single energy level. Hence, they become practically indistinguishable and all behave in a collective way. They don't move or bombard each other, but they are in complete unison. This means that there is zero friction between them. This also means that the liquid can climb up the walls of the container. This is indeed very important since this enables us to see a purely quantum phenomena with our eyes. The superfluid phase, where heat is transferred without a thermal gradient and mass flows without a driving pressure, is a macroscopic manifestation of microscopic quantum effects governing the behavior of atoms. Many of the sources suggest quite strongly that the so-called lambda phase transition at 2.17 Kelvin from normal helium-1 to superfluid helium-2 indicates Bose-Einstein condensation. One reason given that is that the temperature at which it occurs is comparable in magnitude to the temperature for Bose-Einstein condensation in a corresponding system of non-interacting particles. In practice, since superfluidity is always caused by the creation of some Bose-Einstein condensate, in a very broad sense including condensation of Cooper pairs, people sometimes use both almost interchangeably. However, there are edge cases in which they are both different. One of these cases is a non-interacting Bose gas. As a result, sometimes one will also see the following distinction made. A system in which the particles have no or negligible interactions is called a Bose-Einstein condensate, while a strongly interacting system that condenses is called a superfluid. So, for example, a trapped dilute alkali gas is even called a Bose-Einstein condensate, but He4 is called a superfluid. There is no hard cutoff between the two terms. It is a part of the world of ultra-cold phenomena that has won theoretical and experimental physicists alike won several Nobel Prizes too. Liquid helium has fascinated physicists ever since Camelin-Ons liquefied the last of the so-called permanent gas in 1908. In 1913, Camelin-Ons won the Nobel Prize for his low temperature work resulting in production of liquid helium. However, evidence of what is without doubt the most fascinating property of this unique liquid, superfluidity, was not reported until almost 25 years later. Superfluidity was originally discovered in liquid helium by Piotr Kapitsa and John Fallon. The Nobel Prize in Physics 1996 was awarded jointly to David M. Lee, Douglas D. Osheroff, and Robert C. Richardson for the discovery of superfluidity in helium-3. Bose-Einstein condensation was first proposed by London as the microscopic explanation for these fascinating phenomena. Helium-3 and helium-4 exhibit this. Helium-4 has 2 protons, 2 neutrons and 2 electrons. Protons and neutrons are fermions with half-integral spins, and to exist together they must have opposite spins. So their spins cancel each other out, making the helium-4 nucleus have 0 spin. And so the atom behaves like a boson. And more than one particle can have the same energy. These kind of atoms can behave as a superfluid. Helium-3 is actually a fermion as there is only 1 neutron and 2 protons. So the nucleus has a net half integral spin, but 2 helium-3 atoms can combine together to form a Cooper pair, and hence it can also behave as a superfluid, but the properties of both differ. There is a dramatic transformation when the liquid helium cools and reaches near absolute zero. Suddenly you see that the bubbling stops and the surface of the liquid helium is completely still. Now it has turned into a superfluid. The reason for this behavior is that the thermal conductivity increases by a factor of about 106 at the transition, so that the superfluid is no longer able to sustain a temperature gradient to make a bubble. Heat has to locally vaporize the fluid and make it much more hotter than the surrounding fluid. This is no longer possible in the superfluid state. Here is a beaker with an unglazed ceramic bottom of ultrafine porosity. Ordinarily, this container which has tiny pores can hold liquid helium, but the moment the helium turns into superfluid, it leaks through, as you can see. This kind of flow is called the superflow. It appears to defy gravity, and the thin film can climb up the walls of the container. This is why I told you that superfluid has zero viscosity. It can even produce a frictionless fountain. So, after all those discussions and explanations, I really hope that you guys have some basic idea about Bose-Einstein condensate and liquid helium. So if you are thinking that this is the end of the video, then I just wish that you guys don't feel disappointed when I say that there is one more thing worth of discussion before the end. Remember the engineered quantum mechanics box we were talking about in the very first beginning? To recap the same, NASA sent a box of lasers up to the International Space Stations 2 years ago to create a Bose-Einstein condensate, also known as the fifth state of matter. So this type of matter consists of clouds of few million atoms that have been chilled with lasers inside a vacuum to temperatures even lower than in interstellar space. So as we have already learned, these atoms would start to lose their individuality and blob together at such super low temperatures. Therefore, the box's lasers fittingly is called the cold atom laboratory. Going to space to create the fifth form of matter is more of a successful and a consistent way as microgravity comes in handy. The Bose-Einstein condensate created in the cold lab in the space station provides the researchers opportunities to examine the ultra-cool matter for long periods of time than on Earth. The first pure Bose-Einstein condensate was created by Eric Cornell and Carl Weinman on 5th June 1995. They cooled a dilute vapor of approximately 2000 rubidium-87 atoms to below 170 nanokelvin using a combination of laser cooling and magnetic evaporative cooling. What they did was to cool the atoms taken in a little bowl to very low temperature using lasers, but that the temperature was not sufficient to obtain the Bose-Einstein condensate. Therefore, the lasers were turned off and the still not cold enough atoms were subjected to very strong magnetic fields. Now, the hot atoms slop over the edges of the bowl and the remaining ones gets colder and colder. And in this way, they were able to reach the temperature necessary to see the Bose-Einstein condensation. But the problem was the condensate's lifespan. Gravity makes them difficult to study. It yanks them to the ground, making them disappear within fraction of a second. The cold atom laboratory has endless microgravity, so it can collect data for years. It is completely remote controlled. Researchers are getting to make Bose-Einstein condensate on a daily basis, literally sitting inside their living room. How awesome is that?